Okay, back in chapter 16, part 3. And now in this part, we're going to be talking about our absolute dating method. So we're actually going to see how we can put an exact value on events. And we do so by what's known as radioactive decay. So radioactive decay is the spontaneous change of an atom to an atom of a different element by emission of a particle from its nucleus. You have alpha or beta decay or by electron capture. It was developed in 1903 by Marie and Pierre Curie. So we have three types of radioactive decay. The first type is our alpha decay, which you can see in that top picture. In alpha decay, 2 protons and 2 neutrons are emitted with the loss of 2 atomic numbers and 4 atomic mass numbers. The middle picture shows your beta decay, and that's when an electron is emitted from a neutron, which changes to a proton. Your atomic number is going to increase by 1. And then the last picture at the bottom shows electron capture. That's when a proton captures an electron from an electron shell, creating a neutron. So your atomic number decreases by 1. Now with our absolute dating methods, our radioactive elements can undergo one or several of the decay steps. We have what we call the parent element. That is your original unstable element. The daughter element is the product of the radioactive decay, and your half-life is the time required for half of the original number of radioactive atoms of an element to decay to a stable daughter element. It is not a linear rate. It is a geometric rate. So let's look at this diagram on the right. So we start off with 16 units of parent, 0 units of daughter. After one half-life, notice we now have 8 units of parent and 8 units of daughter. So we're going down by half. After another half-life, we now have 4 units of parent and 12 units of daughter. Another half-life, we have 2 units of parent, 14 units of daughter. And then after another one, we have 1 unit of parent and 15 units of daughter. So you can see as your parent decreases, your daughter increases. Now, the most accurate radiometric dates are obtained from our igneous rocks. Our cooling magma, so when your magma cools, your radioactive parent atoms are separated from your daughter atoms. Some of the parent atoms are incorporated into certain minerals during crystallization, but not the daughter atoms. So by measuring the parent to daughter ratio, knowing the half-life of the parent, we can then calculate the age of the sample that contains the radioactive element. The parent-daughter ratio is determined by what's known as a mass spec. It's an instrument that measures the proportion of atoms of different masses. Now, to obtain accurate radiometric dates, we have to be sure that we're dealing with a closed system. And by that I mean that neither the parent nor the daughter atoms have been added or removed from the system since crystallization. So the ratio between them results only from radioactive decay. Now, the leakage of the parent or daughter can occur under your metamorphic conditions. So if we have leakage, we cannot accurately measure the time of initial crystallization. What happens, it drives the daughter atoms out of the mineral into the surrounding rock. So that's why it's difficult to date your metamorphic rocks. Now, with your absolute dating methods, there are certain elements that are easier to use. So our older rocks, we use uranium lead, we use thorium lead, or we use rubidium strontium. Now, we can use potassium argon, that series, when we're dealing with fine-grained volcanic rocks, when our individual crystals cannot be separated. And you can see in table 16.1, you have 5 of the principal long-lived radioactive isotope pairs that are typically used in radiometric dating. We can also use what's known as carbon-14 dating. Now, carbon-14 dating is based upon the ratio of carbon-14 to carbon-12, and it's used to date material that was once alive. So we know carbon-14 has a half-life of 5,730 years. Carbon-14 is only useful back unto about 70,000 years. Carbon-14 is formed from nitrogen in the atmosphere, and the rate's going to vary somewhat. Carbon-14 is actually absorbed by organisms. Once that organism dies, the carbon-14 is no longer produced. So we're able to determine how long has it been since that organism, since that bone fragment has died. And that's what we would use carbon-14 dating for. Okay, this ends part 3 of chapter 16.